Alright, the final example where we have the second derivative of x with respect to t plus 4 times the first derivative of x with respect to t plus 8x is 0, and we have our initial conditions where only x0 is 1 and x prime of 0, so the first derivative of x in 0 is equal to 0. Now, step 1, take the Laplace transform, and I'll write it out in one go this time. So we have s squared times x minus s times x0, which is 1, minus x prime of 0, which is 0, so that we're done there, plus 4 times the first derivative, so that's s of x minus 1 plus 8x equals 0. So we have the Laplace transform here now. Second step is to isolate our x, and well, let's see. We have 3 terms with x. We have an s squared term here. We have 4s times x plus 8x. So the terms with x in them are s squared plus 4s plus 8 times x, and then we are left with a minus s here, minus s minus 4 equals 0. We'll take this minus s and minus 4 and take it to the other side, and we will then divide by s squared plus 4s plus 8, and I'll do those both steps in one go. So we get s plus 4. So if we take this to the other side, we'll get s plus 4 divided over s squared plus 4s plus 8. And we are done with our with the isolation of x. Now we need to rewrite this in something we can use the Laplace table on, for using the inverse Laplace transform. But first we need to see, well, is this something we can factor into two linear factors, or will it have complex roots? Well, if we take 4 squared minus 4 times 1 times 8, it will yield a negative number. Huh? So what I'm looking at is b squared minus 4ac. This is what I'm doing in my head. B is 4, a is 1, and c is 8. And so this will yield a negative number. So it will have complex roots, which means we will not factorize this, but we'll use something else. We'll use the technique of completing the square, where we'll write this as s plus 2 squared plus 2 squared. Now, how did I get to this? S squared plus 4s plus 8. Well, I know I have an s squared and I have 4s, so there's something I can do with s plus 2 squared. But s plus 2 squared is s squared plus 4s plus 4, so I'm left with 4 to be added to make up this 8. Well, 4 happens to be 2 squared, and of course these examples are tailor-made for this, these exercises. In real life they won't be as easy, but it's the same. They might be different values, but it's the same technique. And usually we'll use computers anyway, but you have to go through this to be able to work with the real life systems and the software you might be using. Now, so we have written the denominator in this form, which means we'll be looking for things like s plus 2 over s plus 2 squared plus 2 squared, and some form of 2 over s plus 2 squared plus 2 squared, because these are known things of our Laplace transform. Because if we have something of this, the denominator of this form, we know that e to the power of minus 2 sine of t, 2t, is equal to, let's see, 2 over, the Laplace transform of this is 2 over s plus 2 squared plus 2, and the Laplace transform of e to the power of minus 2t cosine 2t is s plus 2 over s plus 2 squared plus 2 squared. And the general form of it, if we take our trusty book and we look at the Laplace transform, it's always good to have this Laplace table handy. You will be able to have it on the exam. Is that, well, I didn't need the book, but it's on page 1098, is that the general form of this, the Laplace transform of e to the power of minus at sine of b times t, where is it, is b over s plus a squared plus b squared. And the Laplace transform of e to the power of minus at cosine of bt is s plus a over s plus a squared plus b squared. So these are the two things we find in our table, and those are also the two things where we have this denominator. So if we have a denominator of this form, we have to realize that we're looking for things of this form, and because our a here is 2 and our b here is 2, we know we're looking for these two forms. So I'll be wanting to write this one out in terms of these two, and the first thing you do is if you're at this point, and let me just remove this, is we have s plus 4 here. I'll also remove this. So I can write s plus 4 as s plus 2 plus 2. Now for this particular example, this 2 is very convenient. But if that is not 2, but let's say 5, you can always write this as 5 divided by 2 times 2. And then I have something again in this form. Now we don't need to do this here. I've covered that in a different example and it will show up on the exercises. But I can write this as s plus 2 over s plus 2 squared plus 2 squared plus 2 over s plus 2 squared over plus 2 squared. And these two are now in the right form. Where we can use the inverse Laplace transform. So if we take the final step 3, we know that xt is e to the power of minus 2t cosine of 2t plus e to the power of minus 2t sine of 2t. And so if you have something of this form, you know you're going to have to separate it out into these two forms because of the denominator. So we use the these two entries of the Laplace table. So and in our case, a is 2, b is 2. So we have these two things, and we have to rewrite what we have into the sum of the a part in this form and a part in that form. But luckily, this example makes it easy because we have s plus 2 here and 2 here, which make it exactly like the Laplace table, and we can write out our solution.